In this lesson, we start solving problems that deal with things moving, and you start to use that dy dx symbol again. I covered this in the first video for 307, which was implicit differentiation. That's when you started to use the dy dx, and I wanted to help you understand why you did that and what it means. So I want to just cover it again real quick, and we'll talk about vocabulary words, independent variable and dependent variable, which you learned probably the very first day of Algebra 1, probably made no sense, and you just moved on from that and started solving for x, and you haven't seen it since or used it since. It's actually very important. So when you're dealing with x and y, the x coordinates are always the independent variable, and the y values are always dependent on the x. So here's a real life example. This is a screenshot I took from, I think it's the NOAA website of ocean tides. I live near Fort Myers Beach, and I'm a nerd and I'll go check the website before we go to the beach and see if it's low tide. So the denominator, oh, denominator, it's the bottom. Anyway, the bottom here is the x-axis, which represents time in hours. It's military time. And the y-axis here represents feet, in this case, above sea level. So notice that the x-axis represents time. It's the independent variable, and the y-axis is a measurement of some kind. So think about in terms of the ocean tides, the height of the water will depend on what time it is, not the other way around. Like the water does not dictate the time. It's the height of the water depends on what time of day it is. So independent variable in this case is the x-axis, which also happens to be time. So when you're dealing with related rates problems, pay close attention to the words with respect to, because that's always the independent variable. And the x-axis and time are almost always the independent variable when it's not clearly stated. Sometimes it says with respect to something else, like a radius, because in this section, you're not necessarily going to be using XY coordinate situations. Like you'll be dealing with like a cylinder moving and things like that. So you're not really on a coordinate plane anymore. But things are usually done with respect to time. So I want to talk about how to take the derivative using these symbols again. So let's pretend that you're taking the derivative using the power rule. And this is like easy stuff now. The derivative here would just be 2x. But I want you to think of it in terms of taking the derivative implicitly, meaning doing it to everything. Like when you take the derivative of this, you shouldn't be doing it to the 2x only. You're taking the derivative of everything. Just like you would square both sides of an equation or square root both sides, everything has to be done equally on both sides of the equal sign. So really, you're using the power rule for both sides. You're going to be using the power rule here, which is y to the first power, and then you'll use the power rule here. Now, we're dealing with xy in this situation, so x is our independent variable. So when we do the derivative of each of these variables, we're doing things with respect to x. So the derivative actually looks like this. This part is the power rule, which is you bring the 1 down and then you subtract 1, you get 0. And then this piece is stating that you just took the derivative of y and you did it with respect to x. The bottom of that fraction there is the independent variable. The top of that fraction represents the variable that you just took the derivative of. So same thing. We have a 2, it goes out front. We subtract 1. That gives us 2x to the first power. The next piece happens. We just took the derivative of an x variable and we did it with respect to x in this case. So the denominator variable is the independent variable that you're doing things with respect to. In most cases, it's going to be time in this chapter or this section. Sometimes it's other things. So you have to just read really carefully what they're giving you. And then the top variable here is the variable that you just took the derivative of. So notice though that when you take the derivative of the independent variable, you really just get a 1. Like this is like a fraction. You'll learn later, you'll learn some differential equations later, and you'll learn that those are kind of like fractions, and dx over dx is really a 1. So you don't really need to write that dx every time you take the derivative of an independent variable in whatever situation you're dealing with. You don't have to write it, but you really need to get used to making sure when you take the derivative of any variable that you're doing it with respect to the independent. So you may have to put a symbol that looks like this, and it might be dt on the bottom instead of dx. So where you're used to seeing like y prime equals 2x as your final answer here, it's really the derivative of y with respect to x is equal to 2x. Okay, so that's my intro of why you use those symbols. We're going to see why you need them now. Let's do a problem. A rectangular box has a square base with an edge length of x centimeters and a height of h centimeters. So it's square, where it has an x and an x as the base for the bottom lengths, and the height is h. Find the rate at which the volume of the box is changing when the edge length is 8, the edge length of the base is decreasing at a rate of 2 centimeters per minute, the height is 7, and the height is increasing at a rate of 3 centimeters per minute. Okay, so there's a ton of information here. Ton. First of all, when you do these kinds of problems, it's important to figure out what they're asking. In this case, they're talking about the rate at which the volume of the box is changing. When you're talking about the rate of something moving, we're talking derivatives. So when they give us the edge length of the box is decreasing, that's a derivative. When they're telling us the height is increasing, that's a derivative. When they're asking us to find the rate of the volume, that's a derivative. So you just have to start labeling the information you're given. So the question is asking, what is the volume of the box? And we're talking about time here. Notice we're talking about how fast it's moving. So the independent variable is t, and the rate at which the volume is changing would be the derivative of volume with respect to time. So that's what we're finally going to answer. So we need to eventually get a volume equation and take the derivative of it. They also gave us the x value. X is 8. They told us that the x value is getting smaller at a rate of 2. So that's -2, and that would be the derivative of x with respect to time. So when they give you a value, we state that, and then when they tell you when that value is moving, that's its derivative. So the same thing goes for the height. They told us the height was 7, and they told us it was getting bigger at a rate of 3 centimeters per minute. So that's the derivative of the height with respect to time. So we have a lot of information here. What we don't have is a volume equation. Volume would be length times width times height. It's going to look like x squared times h. So to take the derivative of this, we're going to need to use the product rule. The product rule, because x and h are two different functions or two different values. We don't know what those are. So we have to treat them separately. So we need the product rule. So again, we need to think about taking the derivative of each variable with respect to the independent variable. So this is really a v to the first power. So the first piece would be 1 times v to the 0 power, because that's the power rule right there. You bring the exponent down and then subtract 1. And then we just use the power rule, which is the derivative of v with respect to time. That gives us this piece right here. And then the product rule is the first times the derivative of the second plus the second times the derivative of the first. So the first is x squared, so that one doesn't change. The derivative of the second, well, that's h to the first power. It's the same thing. It's the same thing as this v to the first power. It's going to look like 1 times h to the 0 power. Anything to the 0 power is just 1. But we had to take the derivative of an h and did it with respect to time. So every time you take the derivative of a variable, you have to state what you're doing. You have to state that you're doing it with respect to whatever. And because we're talking about time in this case, the dt is the denominator here. Okay, so then first times derivative of second plus second times derivative of first. So the second is the h, the first is the derivative of 2x, or I'm sorry, the derivative of x squared is 2x. And then again, we just took the derivative of an x and we're doing it with respect to time. So that's our product rule. Let me clean it up for you real quick so you can see what it looks like without all my writing on it on top of it. Because the next step, they actually gave us everything. They gave us everything we need. We have an x value, it's 8. We have the rate at which the height is moving, that's 3. They gave us the height, that's 7. There's x again, and then we also know the rate at which the edges are moving. So we have all those values to plug in. Question is asking for the derivative of the volume. So plug it all in, simplify it, you get negative 32. It's really important now not to just stop and leave it like that. We're talking about things moving with respect to time, so use the units. And because it's negative, that means the volume of the box is getting smaller. I mean, think about it. If the edges are decreasing, that means it's going in, like these are getting smaller and smaller. So the square is getting smaller while the height is getting bigger. So this is getting like taller and skinnier, I guess you can say. But which means that the volume of the box is actually decreasing because it's a negative value here. All right, I hope that helps. We got a couple more videos that go over some examples like this.